If you are listening to us right now, you are holding a piece of hardware, a phone, a tablet, maybe a computer, that operates under a strict silent treaty.
Hmm.
Every sophisticated interaction, every image, every single word on your screen, it all comes down to a fundamental consensus.
And that consensus is built on two, and only two, simple opposing states, a 0 and a 1.
Exactly. And today we are fulfilling our mission for you, the learner, who wants to dive into the absolute core architecture of the digital world.
We're going to try and peel back the layers of complexity, to reveal the surprising simplicity that's really at the foundation of everything.
We've been immersed in the source material for this deep dive. It's excerpts from Binary Logic, The Art of Digital Encoding. And for me, the real epiphany isn't just that computers use zeros and ones. We all kind of know that.
Right.
It's why they must, and how the entire digital universe is, well, an ongoing negotiation about what those patterns of zeros and ones actually mean.
And that's our goal for you today. To unpack this secret language, we want you to understand the rules and the agreements, the protocols that take a simple electrical state,
Off or on.
off or on, and transform it into the high-fidelity experiences that we just completely take for granted.
Yeah, and that's the central tension, isn't it? How can something as rich, as incredibly detailed as streaming a 4K video,
Or running a complex scientific simulation.
how can all of that be constructed entirely from just two opposing choices?
It seems impossible.
It seems like a mathematical constraint that's being imposed on an infinite world of ideas. It's like, how do you paint a masterpiece with just black and white? Okay, let's unpack this.
Let's do it.
And I think we have to start at the level of raw physical reality.
Absolutely. So we begin with the bit, short for binary digit. It's the fundamental indivisible unit of information.
The atom of the digital world.
The atom, exactly. And it possesses only two possible states, 0 or 1. Now, this much is pretty well known, but what the source material really underscores, and what's so crucial for this deep dive, is that the choice of binary is not simply a mathematical convenience.
It's not just because it's elegant math.
No, not at all. It is unequivocally an engineering survival strategy.
That phrase, survival strategy, really resonates. Why is surviving the noise of reality more important than, say, using a tertiary system?
Like a base 3 system.
Yeah, 0, 1, and 2. Logically, 3 states should be more efficient than 2. You could pack more information into a single signal.
And mathematically, you'd be right. A base 3 or ternary system is theoretically more compact for storing data, but that logic immediately collides with the messy, noisy reality of electronics.
Right, this is an abstract math. It's happening inside a physical chip.
Exactly. Digital systems rely on physical hardware, transistors, capacitors, wires, and they express these zeros and ones using electrical voltage.
So in a simple binary system, you might set a threshold. Let's say anything below 1 volt is a 0, and anything above 4 volts is a 1.
Yep.
And that leaves you with this massive middle ground from 1 to 4 volts. That's just a disallowed zone. It's a buffer.
Precisely. And if we stick to some historical voltage levels, like the old TTR standards, a 0 might be around 0.8 volts and a 1 is 5 volts. That gives you a 4.2 volt separation between your two states.
That's a huge margin.
It is. Now consider all the sources of error that chip designers are constantly fighting every single millisecond. You've got thermal noise.
Which is just random electron movement from heat.
Yes, just the atoms vibrating.
Yeah.
Then you have electromagnetic interference or crosstalk from adjacent traces on the circuit board bleeding into each other. And then you have just basic component imperfection. No two transistors are perfectly identical.
And all these factors are conspiring to corrupt the signal. So a perfect 5-volt signal that you send might arrive at the receiving gate as, say, 4.7 volts.
Right. But the binary system is specifically designed to tolerate that kind of imperfection. With that massive 4.2 volt separation, if your signal arrives at 4.7 volts, the receiving circuit, which only needs to distinguish if the voltage is closer to 0 or closer to 5, can reliably and instantly categorize it as blown.
Ah, okay. That massive margin of error is the key to stability.
That is the survival strategy in action. You're sacrificing theoretical data density for absolute rock-solid reliability.
So if we tried to introduce that third state, our 2 foots, and represent it with an intermediate voltage, say 2.5 volts,
well, then that generous safety buffer just vanishes.
it becomes catastrophic.
Completely. Because if the true signal is 2.5 volts, but some thermal noise or crosstalk nudges it by just half a volt, the signal now arrives at 3.0 volts.
And the receiver has to make a split-second decision.
And it's a hard one. Is 3.0 volts closer to the 2 state at 2.5, or is it closer to the 1 state at 5? The difference between your target states is now tiny, maybe only a couple of volts. The system becomes exquisitely sensitive to any random interference.
And reliability just plummets.
It has to. When you're processing billions of these decisions every single second, you have to ensure that every single one is dependable. There's no room for ambiguity.
That completely reframes the whole discussion for me. Binary isn't about being smart or mathematically elegant. It's about being robust.
It's about being tough.
It's about engineering systems that tolerate failure by design, recognizing that physical reality is noisy and imperfect.
Exactly. And even though modern microprocessors operate at much lower voltages now, sometimes down to 1.2 volts or even less, the principle remains identical. The ratio of that noise floor to the voltage margin is what's crucial. Binary gives engineers the largest possible signal-to-noise ratio for their basic logic decision.
And that reliability, which seems so simple, is the foundation that allows for all the astronomical complexity we build on top of it.
It's the bedrock.
A single bit, though, is still a very, very small piece of information. It's just a light switch, on or off,
Yeah.
a yes or a no. To build anything meaningful, we have to start grouping these decisions together.
Absolutely. One bit on its own defines a single point. But 8 bits define a whole universe of possibilities.
And that brings us from the bit to the standard grouping that everyone's heard of, the byte. Historically, this settled on 8 bits. So let's walk through the power of that standardization for you, the learner. We can assume you already know the definitions of kilobyte and gigabyte, so let's focus on the functional implication. Why 8?
The 8-bit byte is foundational because of the capacity it provides. It's 2 to the power of 8, which gives you 256 distinct possible values, ranging from the number 0 to 255.
And the choice of 8 bits and therefore 256 values wasn't random, was it?
Not at all. It was a very pragmatic choice made back in the 1960s, and it was largely driven by the needs of early character encoding.
Okay, so why was 256 the magical minimum number needed to standardize meaningful content back then? What did it need to cover?
Well, it provided just enough range to encompass all the necessary components of the English language keyboard. You have 26 lowercase letters, 26 uppercase.
That's 52.
Right. Then your 10 numeric digits, 0 through 9. Then a whole rich array of punctuation, commas, periods, question marks, and so on. But most critically, it had to include 32 special control characters.
So what were those for?
Things like tab, carriage return, and line feed. These were commands necessary for controlling early printers and teletype terminals. They weren't characters you'd see, but instructions for the hardware.
So if you had anything less than 256 combinations, you couldn't even standardize a basic printed document.
You couldn't. The byte became the atomic unit of computation, not just because of the math, but because it satisfied the immediate practical needs of early communication and printing.
So the byte is the fundamental unit of meaning. It's the irreducible building block for data, because 256 combinations was the practical minimum needed for a, well, at the time, a globally standard alphabet.
And this standardization is what allows the entire data mountain to be built. When we scale this, we move into the realm of kilobytes, megabytes, and gigabytes, which are, at the end of the day, just larger and larger collections of these standard 8-bit decisions.
Right, and we don't need to dwell on the definition of a gigabyte, but I think we do need to fully appreciate the scale and the exponential power required to get to that capacity. A kilobyte is roughly 1,024 characters, maybe a short email.
Right.
A megabyte is over 1 million characters. That's a whole novel.
And a gigabyte pushes us past 1 billion bytes. But let's put that into perspective using the complexity of the data itself. Think about a high-definition photograph you take on your phone that might easily consume 10 megabytes.
Okay, so that's 10 million 8-bit bytes.
Which means it's 80 million individual 0 or 1 decisions, just to define the light, the shadow, and the color of that single image.
And here's where it gets really interesting. When you hold a modern device, say a phone with 512 gigabytes of storage, you are holding a machine capable of storing over 4 trillion of those fundamental 0-1 decisions.
The scale is mind-boggling.
And the entire architecture works because the reliability of that base unit, the bit, allows for this exponential scaling of complexity up to the gigabyte and beyond. The simplicity is a feature, not a bug. It enables this massive capacity. But all that capacity, all 4 trillion of those bits, is completely worthless without the next step, the rules for interpretation.
Yes. If Section 1 was about the physical requirements and the math of grouping bits, Section 2 is the crucial conceptual leap, This is where we get into semantics.
Into meaning.
Exactly. We're moving from raw data, which is just a series of electrical pulses, to semantic content, something that holds meaning for a human being.
And meaning, as we just established, is not inherent in the uses and ones themselves. The sequence 01000001 is just a pattern.
It's just a number, 65, in decimal.
Right. And it only represents the uppercase letter A if everyone on the planet, or at least every computer on the planet, agrees to use the same translation manual.
That is the power of encoding rules. They are these agreed-upon standards that dictate what a specific pattern of bits represents. If the rulebook says, when you see the pattern 0100000001 display an A, then the system works.
But if you swap that rulebook out for another one,
The data stream, the bits, remain identical, but the output becomes garbage. Total nonsense.
it's the difference between seeing the symbols on a sheet of music and hearing the symphony. The notes are just symbols on a page. The symphony is the collective, agreed-upon interpretation of those symbols by the orchestra.
That is a perfect analogy. And this standardization is what created the interoperable digital world we live in. It's what allows you to send an email from Windows PC to someone using a Mac or a Linux machine.
Even though the underlying operating systems might be radically different.
Radically different, but they all respect the same fundamental encoding rule for text.
So let's apply this to text, because that's the historical battlefield for these encoding rules. Text encoding just maps specific numerical values to specific characters.
And the initial success story, the one that really established the necessity of these agreements, was ASCII, the American Standard Code for Information Interchange.
And its big innovation was to formalize the mapping of 128 characters using just 7 bits.
Which seems strange because we just talked about the 8-bit byte.
Right, the genius of ASCII wasn't just its scope, but its constraint. By using only 7 of the 8 bits, it left that 8th, final, crucial bit of the byte free.
Free for what?
Well, for potential error checking or customization by different manufacturers. It was a clever bit of future-proofing.
That's a fascinating architectural detail that people often overlook. It was incredibly efficient for its time, but as you noted, it was deeply rooted in the Anglosphere. Its 128 character limit meant it couldn't handle the louts of German.
Or the tills of Spanish, or the currency symbols of global finance, like the pound or yen sign.
It became a computational bottleneck almost as soon as computing started to go global.
And that led to chaos, right? This proliferation of extended ASCII variants where everyone decided to finally use that 8th bit to provide 256 characters.
But everyone had their own idea of what those extra characters should be. So if a computer in Germany assigned the number 164 to the character A, the A umlaut,
A computer in Portugal might assign that exact same number, 164, to the character ñ, the n tilt.
and when those two computers tried to exchange files, you got what's known as the Mojibake problem.
Scrambled text, gibberish.
Exactly. The bits were transmitted perfectly correctly, but the decoding rules, the rule books, were different, and that led to corrupted data. The internet, which connects literally every language system on Earth, absolutely required a universal solution that could map every known character set without any conflict.
And that modern solution, which really defined a new era of digital universality, is Unicode.
Right. Unicode didn't just expand ASCII, it threw out the entire 8-bit constraint. It created a truly universal standard, and it uses a varying number of bytes, sometimes up to 4, to define a single character.
Which allowed for an address space of over 1 million distinct characters.
It's massive. It covers virtually all the world's historical and modern writing systems. Chinese, Arabic, Hindi, Cyrillic, plus an ever-growing library of symbols.
And I think the most relatable connection to the user experience for you today is the emoji. The source material highlights this as the perfect, living example of encoding in action.
It's a great example. When you send the face with tears of joy emoji,
Yeah.
you are not sending a tiny picture.
What are you sending?
You are sending a numerical code, specifically U plus 1F602. This code is defined and governed by the Unicode Consortium. Your device encodes that number into a specific sequence of bytes, often 4 bytes in the UTF-8 standard,
And the recipient's phone receives those 4 bytes.
recognizes them as the Unicode standard code for U plus 1F602, and then it uses its own operating system's font library to display the graphical representation of that emoji.
Which means that the little picture you see, the graphical interpretation, might look different on an iPhone versus an Android device.
It almost always does.
But the underlying numerical code, the bits being transmitted across the network, are absolutely identical.
The meaning persists, regardless of the aesthetic presentation. That is the essence of standardized encoding. It provides character permanence.
And you mentioned UTF-8. That's another really clever bit of engineering.
It is. The UTF-8 implementation, which is the most common way Unicode is encoded and transmitted over the web today, is a beautiful example of clever bit arrangement. It uses variable lengths.
Meaning?
If the character is simple English, it just uses 1 byte, which maintains perfect backward compatibility with old ASCII systems.
Oh, that's smart.
But if it's a more complex character, like a Chinese character or an emoji, it automatically scales up to use 2, 3, or even 4 bytes as needed.
So it's a dynamic, adaptive system, a
Yeah.
silent negotiation happening billions of times a day just to ensure that the letter T remains T and that the smiley face remains the correct smiley face.
And this foundation is what all complex media must then be layered on top of.
Okay, so moving from text where the meaning is symbolic to rich media like images and sound, where the meaning is related to physics and perception, that requires a massive scaling up of these encoding rules. How do we translate light, shadow, and sound waves into zeros and ones?
The fundamental principle is exactly the same. We have to translate a physical, continuous phenomenon into a stream of discrete numbers. For images, we're converting continuous light reflection into a spatial array of numbers.
Let's start with images. A digital picture is just a mosaic of tiny cells, right? Pixels.
Correct. Each individual pixel is assigned a set of color values, and typically we use the RGB model, red, green, and blue intensity. To define the quality of that color, we assign a specific number of bits, what's called the bit depth, to each of those 3 channels.
The source material often talks about 24-bit color, so let's walk through what that 24-bit system actually means in terms of the numerical range and what the viewer actually sees.
Sure. 24-bit color, which is often called true color, dedicates 8 bits to the red channel, 8 bits to the green channel, and 8 bits to the blue channel.
So 3 times 8 is 24.
Exactly. And since we know that 8 bits gives us 256 distinct values, 0 to 255, this means the intensity of red can be one of 256 shades, green can be one of 256 shades, and so on.
Which gives us that staggering 256 times 256 times 256 combination.
Which results in 16,707,216 distinct colors. And that is the necessary threshold, the number that engineers agreed upon, to ensure that the human eye cannot perceive the transitions between shades.
So you don't see that ugly banding or stepping in gradients like in a picture of a sunset.
Precisely. So if you look at a photograph of a sunset, every single pixel, and there might be 20 million of them in a modern camera, is defined by 24 bits, or 3 separate 8-bit numbers, all working in concert to define one tiny dot of color. The path is immutable. Physical reality, the light intensity, is mapped to a number. That number is translated to binary, and that binary is stored as bits.
Now, sophisticated systems often move to 32-bit color, right? What are those extra 8 bits doing?
That's a great question. They aren't usually for more color depth. 16.7 million is plenty for our eyes. Those extra 8 bits are most often used for what's called the alpha channel.
And alpha is transparency.
Transparency. It dictates how see-through a pixel is. This is absolutely critical for layering images, videos, and graphical overlays on our screens. It's a layer of control data that's married directly to the color data for each pixel.
And the data volume becomes enormous, almost immediately. If a 10-megapixel image has 10 million pixels, and each of those pixels requires 3 bytes of color information.
That's 30 million bytes of raw data right there, 30 megabytes. And that's not even counting the file header or any of the compression rules we'll talk about later.
This immense data volume really sets the stage for our discussion on compression.
But the complexity only escalates when we introduce the element of time and move to audio encoding. We are shifting from mapping spatial data, like pixels in an image, to mapping temporal data.
Okay, so how does the incredibly smooth, continuous analog phenomenon of a sound wave, which is just air pressure fluctuating many times a second, get rigidly converted into a stream of zeros and ones?
This is done through a process called sampling. The device, like the microphone in your phone, records the sound by taking rapid, discrete measurements of the air pressure over time. The fundamental theory that governs this conversion is the Nyquist-Shannon sampling theorem.
Okay, let's unpack that theorem. What's the fundamental rule it imposes on digital audio?
The theorem states that to perfectly reconstruct a continuous analog signal, you must sample that signal at a rate that is at least twice the highest frequency present in the signal.
Okay, so human hearing. We can perceive frequencies up to about 20,000 hertz or 20 kilohertz,
Right. So according to the theorem, the sampling rate had to be at least 40 kilohertz, twice that amount.
which explains the standard CD quality sample rate of 44.1 kilohertz. It gives you that necessary buffer above 40 kilohertz to make sure all audible frequencies are captured.
Exactly. So at 44,100 measurements per second, you are converting that continuous wave into 44,100 discrete numbers every single second. That's the temporal component.
But there's another dimension, isn't there? We also have to consider the precision of each of those measurements, the bit depth of the sample.
That's right, like 16-bit audio versus 24-bit audio.
So what does that extra bit depth buy us? What does it mean for the sound?
Bit depth defines the amplitude resolution. That's the difference between the loudest and the quietest sounds we can capture. 16-bit audio provides 2 to the power of 16, or 65,536, distinct numerical levels for the amplitude.
With the volume, basically.
For the volume of each sample, yes. And this corresponds to a dynamic range of about 96 decibels, which is the standard dynamic range for a CD.
And 96 decibels is the range between the quietest sound the CD can represent and the absolute loudest peak.
Correct. For professional audio, 24-bit depth is standard now. That offers over 16 million amplitude levels and a dynamic range of 144 dB.
That's well beyond human hearing.
It is, but it's crucial for recording and mixing engineers because it gives them massive headroom against digital distortion or clipping. So high-fidelity audio is this extremely rapid stream of highly precise numerical measurements, all translated into enormous streams of zeros and ones.
Which, of course, leads us to video. The source material rightly describes this as the grand finale of encoding.
It's the most complex media type because it synthesizes all the previous rules simultaneously.
Video is motion, which is created by showing a rapid succession of static images or frames.
Dot combined with a synchronized audio track and then wrapped in very complex compression. Just think about what a modern video stream demands for every second of 4K video at 60 frames per second.
Okay, so we're rendering 60 individual high-resolution images every second. If 4K is roughly 8 million pixels per frame, and each pixel is 24 bits.
That's 24 million bytes per frame. Multiplied by 60 frames per second, you are looking at 1.44 gigabytes of raw, uncompressed data per second. And that's just for the visual component. Add the high-resolution audio stream on top of that, and the uncompressed data rate is just completely untenable for storage or for streaming.
That is why the source material emphasizes this, is the coordinated choreography of encoded data. It's not just that all this data has to be packaged. The visual data and the audio data have to align perfectly in time.
The file format has to contain incredibly sophisticated synchronization rules. It needs to tell the playback device. Start visual frame number 3450 at the exact microsecond you begin playing audio sample number 1,523,400.
And if the device misses one of those synchronization instructions,
You get lip sync errors. The visual and the auditory components decouple. The entire viewing experience hinges on this silent agreement that dictates perfect timing between these two massive independent streams of data.
it's astonishing how robust the system is, given the sheer magnitude of data points and the complexity of those rules. But the only way we manage those 1.4 gigabytes per second is through the next stage, the art of arrangement and really of compromise.
The lever arrangement, yes.
So we've established that encoding is the process of putting meaning into the bits. Now we need to turn to decoding and file formats, which is the process of recovering that meaning. Why is the file format, the JPEG, the MP4, the DOCX, why is it so critical if the underlying information is just universal binary?
The file format is the interpreter's manual. It's the rule book. A file is not simply a bucket of bits. It is a structured set of instructions and data. The format defines that data structure. It dictates where the content starts, what rules were used to compress it, how many bits define a pixel, and how to sequence all the blocks of data.
So when a program on your computer encounters a file, the first thing it does is look for the metadata, which is often contained in a file header.
That header is everything. It is the agreement made before the content even starts. The header of an MP4 file might declare, I am a video, I was compressed using the H.264 codec, the frame rate is 30 frames per second, the audio is AAC compressed at a 48 kilohertz sample rate. Without that manual at the beginning, the subsequent stream of billions of zeros and ones is completely unintelligible.
And this highlights what the source calls the garbage consequence. If you try to open that MP4 video file with a program that's expecting, say, a ZIP file structure,
It breaks immediately.
the program will try to read the video's header bits as instructions for directory structures and file names, leading to an immediate error. Or worse, a chaotic mess of symbols if the program tries to interpret the binary as text.
And the bits themselves remain the same. The zeros and ones on the disk haven't changed, but the meaning changes entirely based on the decoding rules you apply. The takeaway for you is a strong reminder that your entire digital life is built on these foundational agreements. If the file format standards collapsed, the digital world would revert to incomprehensible noise.
And because of those astronomical data requirements we just talked about, 1.4 gigabytes per second for raw video, the demand for efficiency is just relentless. And this drives the necessity of compression.
Compression is the ultimate act of clever bit arrangement. It's the engineering solution to the problem of exponential data growth. And the core principle is always the same: exploiting redundancy.
Redundancy in images is pretty easy to visualize. The classic example is a blue sky where you have thousands of neighboring pixels that all share the exact same color.
Right.
But how do algorithms find and exploit redundancy in complex dynamic data streams like video and music?
They look for predictability. If a video frame has a stationary background, the algorithm doesn't need to store the color values for that background in frame 2, frame 3, frame 4, and frame 5.
It'd be a waste of space.
A huge waste. So instead, it stores the full data for frame 1, that's called an iframe or an intercoded frame, and then for frame 2, it only stores the difference in the bits from the previous frame.
Which is why video compression relies so heavily on these predictive frames, the P&B frames, which only encode movement or change.
Exactly. This allows you to replace massive chunks of repetitive pixel data with small, efficient instructions like shift the block of pixels representing the subject's head 4 pixels to the right. That's a massive, massive bit saving. And this efficiency is broadly categorized into 2 types, depending on how much we value the original data.
Okay, let's start with the safer bet, lossless compression. The source defines this as compressing without losing any of the original information or quality.
This relies purely on recognizing and rewriting patterns. If you have the sequence 00000001001, instead of storing those 9 bits, a lossless algorithm might rewrite it as an instruction. Repeat the pattern 001 3 times.
And when the file is decompressed, the original sequence is mathematically perfectly recovered without any change.
Exactly. This is absolutely critical for data where integrity is paramount. Things like computer programs, financial logs, scientific data, anything you would put into a ZIP file.
Then we arrive at the pragmatic compromise that allows most of our modern streaming life to exist, lossy compression. This is where we accept a small and hopefully imperceptible reduction in quality in exchange for file size savings that can exceed 90%.
Lossy compression relies entirely on the limitations of human perception. For images, a common technique is chroma subsampling. This is where we recognize that the human eye is far more sensitive to changes in brightness or luminance than it is to subtle shifts in color or chrominance.
So the algorithm reduces the amount of color information it stores, but it keeps the brightness information highly detailed.
That's right, and we don't notice the loss of that color data, but the file size drops dramatically.
And in audio, the technique is called psychoacoustics.
Yes. The MP3 algorithm, for example, uses a model of human hearing, a filter to identify frequencies that will be masked by louder simultaneous sounds. If a very loud bass note is playing, your ear cannot perceive a quiet, high-frequency sound happening at the same time.
So the algorithm looks at those bits.
And it literally deletes the data corresponding to the masked sound. It just throws it away.
The deleted data is gone forever, but the resulting stream is small enough to stream over a mobile connection.
It's a genius trade-off between engineering constraint and human perception.
So it's still bits. It's the same zugers and ers.
Always, but they are arranged more cleverly. The difference between a raw video stream and a compressed MP4 is simply a set of highly sophisticated encoding rules that determine which data points are redundant, which are critical, and which can be discarded without any perceptual penalty. The digital world is defined not by what we store, but by what we agree we don't need to store.
So what does this all mean? We've traveled from the physical necessity of the binary system all the way to the massive complexity of coordinated media streams, all held together by these invisible universal agreements. If we synthesize the core finding one last time for you, it is that digital technology is the art of storing meaning as bits and recovering that meaning using agreed-upon rules.
It really is a testament to standardization. Everything you do on your device, reading a complex document, watching a high-definition movie, sending a complex emoji, it's all a silent, continuous dance of encoding and decoding.
And it all works because that initial fundamental choice of 2 states made the foundation incredibly robust against physical noise.
The structure is robust. The rules are standardized.
But we are now entering a new era of computation. The source material hinted that these specialized workers, the CPUs, the GPUs, and particularly the new breed of AI chips, are beginning to read and interpret these bits using fundamentally different rules.
And this raises a profound question about the future of encoding. Historically, the rules, like ASCII or JPEG, were designed for human consumption and interpretation. The CPU interprets bits based on instructions optimized for serial processing.
One thing after another.
And the GPU interprets them based on coordinates and colors, optimized for parallel rendering, drawing millions of pixels at once.
But AI processors, particularly those designed for deep learning, they often operate under entirely new rules. Rules optimized not for display or for instruction, but for predictive pattern recognition.
And consider this specific technical shift: precision. Traditional computing relied on 32-bit floating point numbers for maximum accuracy. AI models, in their quest for speed and efficiency, often use much, much lower precision.
Like 8-bit or even 4-bit integer quantization?
Exactly. Meaning they deliberately sacrifice 75% or more of the numerical precision, reducing the number of bits used to define a number, all in exchange for speed.
That's a huge trade-off.
It is. They are effectively using smaller bytes, or even nibbles, which are 4 bits, to define the weights and biases in their neural networks. So when an AI chip looks at the bits and picture, it isn't necessarily applying the 24-bit RGB color rule. It might be applying a rule that says these 8 bits relate to the probability of this image containing a cat.
The meaning is transformed. It's no longer color intensity, it's a predictive correlation.
Precisely.
So, are these highly specialized processing units just reading the same standard files using new, more efficient compressed numerical rules?
Sure.
Or, by finding patterns and correlations that are completely invisible to our human-centric encoding rules, are they creating an entirely new binary language that we're just beginning to decode?
That's something for you to mull over. What happens when the agreement about what the numbers mean is no longer centered on human language and perception?
Thank you for joining us on this essential exploration into the language of the digital world. We'll see you next time.